All right. So we are live for AvnaCode 2025, day 8, which drops in 54 minutes. And until then, we are working on 2015 problems. We are almost there. And I think we'll get to the end, but we're going to start hitting some of the tougher problems. Day 17 didn't look too bad, though. This is a classic problem. So we'll go to our day 16 code. And copy that as a template for 17. Alrighty. Oh, thank you. Thank you for the birthday wish. I get 2 birthday screens because of midnight. Okay, so day 17. Basically, we just find all the ways to sum to 150, given these numbers. How many different combinations of containers can exactly fit all 150 liters of eggnog? Okay, so here's our input. We'll parse them to containers. What's the input format? They're just all in a separate line. So we can parse those into numbers and then sort them. Map each to int and then sort. And def count. So we have a goal we're getting to. I'm going to put that in. We know it's 150. Whoops. We know it's 150. I might want to keep that in like the recursive in case I call it with a smaller argument. And we're using some number of containers, some collection of containers. What? So this n is our goal. So we'll rename it as goal. And here's our containers. Okay, so first a base case. If we've already hit our goal, I guess it counts as one way. There's exactly one way to do it, and that is to do nothing. Oh, wait. We need to count. So no, we're going to call this like the remaining bit. Okay, so if goal is equal to 0, then 1. Otherwise, we do actual work. Great, so we can lump this into sub-problems. Let's match on containers. So containers, match. I'm going to put this in a separate line there. So we have C onto C's. And we can recurse with count goal minus C. So as if we use a container. Do we have unlimited numbers of each container? For example, 15, 10, 25. Okay, wait, so there are duplicates. Let me see. Containers. Whoops. Containers dot size. And then we want the distinct size. We want sorted here. Okay. Our worksheets are cooperating today. All right. So there are duplicates, and we can't reuse containers. So we can choose to use this container or not. And if we choose to use a container, we reduce our goal, and then we reduce all of our containers. So the number of ways to do it that way while choosing to use this container, plus the number of ways to do it without choosing to use this container. Um, yeah. So we just maintain the same goal and then still just use the remaining containers. So we've ignored that container. Nothing happened to our goal. Okay, that's fine. And if there are no containers at all to choose from, then, well, we can't hit our goal. So this is 0 in this branch. And that reminds me that if we ever go negative here, then we've also no way to hit our goal. So if goal is less than 0, then 0, else. Alrighty. I think that does it. So we count 150 with our containers, and that's as 1. Right. Um, oh, wait, not containers. Count. There we go. 654 ways. I believe it. Yeah, I can do that problem in my sleep. I can probably drop a line or two by condensing some of these cases, but okay, so part 2. Um, while playing with all containers in the kitchen, another load of eggnog arrives. The shipping and receiving department is requesting as many containers as you can spare. Find the minimum number of containers that can fit all 150 liters. How many different ways can you fill that number of containers and still... Wait. How many different ways can you fill that number of containers? Okay, so now we want... So what we first calculated was the number of ways to do containers, but we didn't actually return any of the potential containers or possible solutions. So now it wants the optimal solution, and there actually could be multiple optimal solutions. So we'll return all of those. So we're just going to modify this count. We'll call it count 2 for now. You could probably use the same code for both, but... So we need a list of solutions, and a solution should look like a list of containers. So a list of int. Okay, so we modify this. If goal is less than 0, then we have 0 solutions. So we just give an empty list. We have to keep track of the current solution we are building, don't we? So we need like a so far argument used. Yeah. So the used containers. So in this case, we just return the used containers that we found. Yeah. Otherwise, we recurse. And in this case, we are concatenating 2 lists. I suppose it's not ideal that I'm using lists. I could be using vectors, but probably the performance won't matter. We'll see. And if there's no way to do it, then we return nil. Okay. So we should be able to get the same as ands 1 by doing count 2 of 150. Oh wait, we need to pass along the used. So this compiles. So used gets passed along in this case because we didn't use any new containers. But in this case here, we're using the container C. So we'll con C onto used when we pass it down. Okay, so now if we do that, and then get the size, it should be 150 as from earlier. Oh, we required a list of mints. Okay, yeah, just a list of used then. Used is already a solution, is what we're saying. And then in this case, we're still turning used into a solution. Too many arguments for method. Oh, we need to recurse with count 2. Alrighty. Okay, great. We get the same answer. So we can use that for part 1. Bad cop, hello. And what we want for part 2, so we'll call this ways, or solutions. Solutions equals that. And I think we can just delete the old version. We can write ands 1 in terms of that new solution. So it's solutions.size. And now, well, the min number solutions is solutions.map.size.min. And then ands2 is how many match that min. So val ands2 equals solutions.count dot size equals min. How did I get into Scala? It's kind of a story from multiple directions. So let's see, before I got into Scala, I was into Python, Java, and Scheme. I was getting into functional programming, learning about it, and I was also really interested in compilers at the time, and I thought it'd be cool to have other languages for the JVM. And then I realized there's Clojure and Scala, and there are other languages. You could actually compile other languages to JVM. And I took to Scala because it seemed like a nice combination of things I'm familiar with. So I like that it's concise like Python. I like that it used objects in a familiar way like Java, and that it enabled functional programming like Scheme. So it's like best of all worlds, and I kind of just went and ran with it. And then once I got into industry, Scala developers are kind of hard to find. So I was always in demand, and just kind of that momentum stayed. So the answer here is 57. Boom. You might be the #1 JVM hater. That's fair. I kind of hate I hate being bound to the JVM. But Scala is not just bound to the JVM. So Scala runs in JS and on native. So it started with JVM. It actually started with JVM and .NET. Believe it or not, they abandoned .NET long ago. And the Scala JS implementation is probably the most faithful JS implementation of the language. There are no surprises there when you're using it. Yes, I'm familiar with Morgan Stanley. They have a massive Scala code base. I've met people that work there. At this point, I'm familiar with most of the big Scala shops. Scala JS is actually really nice. I should do more front end stuff, but it's a nice developer experience if you already know Scala. So if you're like a backend dev and just want to throw up some panels or something, it's handy, really handy. Okay, so 17 was very straightforward. 18 might be a little bit more fun. I remember taking a peek at this yesterday. All right, so now we have a grid of lights and we're making some sort of animation. So start by setting your lights to the included initial configuration, on and off. Okay. This is, okay, here's like initial state. I don't know why these are numbered yet. Um, Bash sadly does not go to JS yet. That'd be nice, wouldn't it? Unless you take Linux along with you, which has been done. Wait, what do you mean? Hey there, Ice Cold Witch. Okay, so they have an example of this. In the 6x6 grid, light mark A has neighbors 1 through 8. Okay. And light B has only 5 neighbors. Okay. The state a light should have next. Okay, it's just a cellular automata. We could probably knock this out pretty quickly. We've done lots of them. Based on its current state plus the number of neighbors that are on. Okay. Okay, so as I do with grid problems, just because it makes everything easier, we don't use 2D vectors. This is just going to be a hash set of points. It makes all the, you don't have to do bounds checking, just, I know. I'm lazy and don't care about performance. Linux can run in JS. Everything can run in JS. ClojureScript is self-hosting. So ClojureScript can compile ClojureScript in the browser, which I think is pretty cool. None of the other compile to JS languages that I know of do that. Hey, Alka. Okay, wait, while we're talking about languages, have you all heard of Unison? Unison language. So it's not it's not really just another language because it's the idea with Unison is that all of your code. Oh, you've heard of it? Yeah, it's really cool. So I mean, 1.0 just came out recently. There's some overlap with the Scala community. Like, the people that developed it used to be Scala developers, or I guess they still are. But they've made the rounds into Scala conferences talking about Unison. But for everyone else who doesn't know, like the main idea is that everything is a a piece of code is identified basically by its hash, not by the lines of code, and then everything is kind of stored in its own database. So your 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 database is aware of like the AST-ish of your code, right? So when you version something, it's not based on like the lines of code or whatever. If you want to call a remote function, you just basically ship the function across. So like version gets very easy because a version of your code is just you reference the code by its hash, right? And there's no getting that wrong. And then of course it's like functional, statically typed, and that's cool. It looks Haskell-ish, like an ML type language. But that's one I want to try out. I might try some translations into Unison. after AOC this year. I mean, you're using GitHub, or like you use Git, right? Git's a data. When I say database, I mean more like what's going on in Git. So when you do Unison, you don't actually. I don't think people use Git with Unison. But yeah, like it's a simple idea, but it has all sorts of cool implications. So just wanted to share that because it's been on my mind. Also, back to this problem. What's the rule? A light which is on stays on when two or three. This is a game of life. Two or three neighbors are on, and turns off otherwise. A light which is off turns on if exactly three. This is game of life. This is totally game of life, right? I'm not missing anything. Cool. Well, I think we want point and area. So let's make this a vector. So we want the bounding area of that input. And then our initial state, val init, is going to be a set of point, and it's going to be area dot points iterator. Wait, let's make sure that compiles. I'm not getting my autocomplete. Area dot bounding. Bounding doesn't apply to that. I wrote this API, I should know. Okay, wait, area. I think I just apply it to grid. Okay, apply it to input. Okay, now we get area that points iterator, and then we're going to filter those points. You're predicting today will be a Dijkstra day? I mean, it's kind of about time, right? I should have like a template for my Dijkstra code. So I don't just, I don't know, I could go back to past copy paste, but I have to remember a day number. So it's good if, let's see, input at that point is a hash, a pound, then that light is on. So that's our initial state and our state transition. We can just do this in an unfold. So we're gonna make it a lazy list, lazy list.unfold. So we have our init state. And oh, we just have our state. So state and a new state. So basically for each state, for each point in state, state.map. Yeah. Anytime I'm building kind of like a series of states, I like to use unfold. It's not really necessary here because unfold carries across your state, but also has like an output. So the A parameter in there is the output, and you're building a list of output from your state. Honestly, I can just do iterate, lazy list.iterate, because there's no end condition here. So unfold is overcomplicating things. So we start with iterate, and then we need a state-to-state function. So state.map. Too late. Too late. Iterate is um, simpler. You made me rethink things, and the rethinking was good. Okay, so we count the adjacent neighbors. So p dot surrounding. Surrounding means 8 surrounding. Adjacent I have it just for the for surrounding. P dot surrounding dot count how many are in the original state. And then we match. Um, I suppose I could just iterate over everything in the area. A light which is off. Okay, yeah, I shouldn't just be iterating on points that are on because points that are off might change. So let's change this a little bit. We're going to take area dot points iterator dot map. So for every point, we look at the surrounding and we count how many. And do we want to keep trimming to the bounding box? I suppose we do want to keep trimming to the bounding box. Okay, so we'll add a filter state there. To do trim to bounding box. So, it doesn't just depend on how many is surrounding it, right? Where's our rules? The light which is on stays on. So we're not just going to match P, but we're going to get P's current state. So state of P and the number that are on surrounding. So this gives us a Boolean, right? So if it is on, and then we have N, where N is a light which is on stays on when 2 or 3 neighbors are on and turns off otherwise. We can just do 2 or 3 here. And I suppose what we want to do here is a filter. So true means on in this case. Great. Now, a light which is on turns false otherwise, or turns off otherwise. Now, light which is off, so we have false here, turns on if exactly 3 neighbors are up. So if there are 3 neighbors, this becomes true. And otherwise, if it is off, then it remains off. Okay, so this is our next state. And then that's it, isn't it? Let's put that in a separate function so that we can test it. So def next state is a set of point, and this returns a new set of point. And we could basically copy all of this here. And we're just going to do set dot. All right. Now our states is just lazy list dot iterate from init with next. Okay, how many lights are on after 100 steps? Oh, wait, to do. We need to trim to surrounding box. Oh, wait, we are already staying trimmed to surrounding box. Cool. Never mind. So states 100 is after 100 steps. So val and 1 equals states 100 dot size. Okay, let's fix some things here. Init, this needs to be a set. Equals set dot from. and 61. Cool. Hey, first time, simple code. This feels satisfying. Okay, so part two. You flip the instructions over, Santa goes on to point out that this is all just an implementation of Conway's game of life. Knew it. At least it was until you notice something's wrong with the grid of lights you bought. 4 lights, one in each corner, are stuck on and can't be turned off. The example above will actually run like this. Okay. Um, all right, so our next function. Well, basically the input state will need to have those 4 corners on. And then afterwards need to make sure those corners are still on. So I think we have corners, area.corners. No, top left. Okay, we have corners. So we're just gonna make a set of point. Set top left, area.top right, area bot left, and area.bot right. Okay, and we can write next to in terms of next one. So basically our incoming state, we're just going to union with corners. So state.union corners. And then we call next. And then again, we union with corners to keep those lights on. And now we just swap out for next two. So and 2 equals states 2. I'm just gonna, yeah, let's make a states 2. Put the corners up here. So states 2, iterate with next 2, and states 2 100 dot size. It's a pretty good delta. Oh, up adds 2. Give it a sec to run. And 1006. Great. Okay, I was expecting that to take me a little bit longer. I'm feeling really good about my warm-up today. 19. Right, this is the graph problem. Okay, let's take a look at this. Isn't this satisfying though? This code was pretty satisfying, I thought. I know you don't all write Scala, but this should be pretty understandable. I'd hope, even if you don't write the language, you can read it. Okay, day 19, medicine for Rudolph. So Rudolph is sick. Red-nosed chemistry is different. The North Pole is equipped with a red-nosed reindeer nuclear fusion fission plant, capable of constructing any red-nosed reindeer molecule that you need. It works by starting off with some input molecule, then doing a series of replacements, one per step, until it has the right molecule. The machine has to be calibrated before it can be used, determining the number of molecules that can be generated in one step from a given starting point. Okay, so suppose these are only replacements. And if we start with HOH, then these can be generated. Okay. Um, that makes sense. So what is the question? Your puzzle input describes all the possible replacements and at the bottom, the medicine molecule for which you need to calibrate the machine. Okay. How many distinct molecules can be created after all the different ways you can do one replacement on the medicine molecule? One replacement. Okay, so this first part at least seems pretty straightforward. We just run the replacements and count. I got warned by Zuno that day 19 is very much beloved. By which I mean it traumatized people. So we'll see what part two brings. Let's take a peek at our input. Okay, and the last the last line is the medicine, followed by all the possible replacements, and at the bottom, the medicine molecule. Okay, so let's parse the replacements as a map. So I'll use these as a template. We'll do our usual input.collect. So about replacements. This could be a map from a string to, I suppose, a list of strings, isn't it? For now, I'll just say string to string. Um, oh, wait. Each of these has multiple replacements. Okay. So input.collect case, what does this look like? So here is string one. So we're going to go A to some B. And we're just going to do a tuple, A to B. And we're just going to group by identity. Group map. So this isn't string to string. This is string to list of string. Group map, identity, and then we're just going to take the second half of the tuple of the normal group by. Found. Hold up. Oh, right. We started with to-do list. Okay. Wait. So we're going to group by the left of the tuple, right? And then we're going to keep the right of the tuple in the right-hand side. So that should work. And then the val medicine is just going to be input.last. Let's make sure that parses properly. That looks right. Cool. Okay. And the problem asks, how many distinct molecules can be created after all the different ways you can do one replacement on the medicine molecule? Okay, so let's just run all the replacements and then do a distinct count. Replacements. Or wait. Um, you know what? I didn't need to turn this into a map of string to list string. I could have just kept, a full list of tuples. But I think I'll continue to live with that because we might need the map structure later on. Um, so given a replacement, now replace. So we have a replacement r from string to string, and it's going to be some list of strings. And we're running this replacement on a molecule. Oh wait, no, this is a tuple here. A tuple of string to string, and then a molecule, which is a string. And then M, we find all instances of the left. So val, I'm not sure I want to write it this way. Let's just take all the replacements. Map. So we have a left. So case left, and then we have a bunch of rights. And then we can take our rights.map. Okay, so now we have a left and a right. And then we can take our medicine. We can turn this whole thing into its own function later if we want. Dot find is there a substring? I want like all occurrences of a substring. I guess index of slice. Get all, I mean, is there like all indices? Okay, so we could just repeatedly do it. Yeah, let's do like a tail recursive search. So starting from an index I. And we are looking for a list of indices. In particular, we want like a list of strings, right? List of all the possible string replacements. So starting at 0, we do medicine dot index of slice being left. We'll change I. We'll name it start so we can use I here. Val I equals that, and then we want medicine dot take. Is there a replace? Dot replace. Replace first. Okay, but I want to be able to give it an index at which to start. What does this do with the char sequence? Replace a string with a string, and it just does the first instance of that string. All right, so I suppose instead of a start index, we're just gonna have to like trim and get the remaining. I don't like that. I want to do like a particular replacement, and I guess there's not a library function for what I'm wanting to do. So I might have to write my own. Okay, fine. So if the slice starts at index, say 1, then we're going to take the first one. So medicine.take1 plus right plus medicine.drop left dot size. So that was the previous one. But also we're dropping what we took originally. So I plus left dot size. Okay, that's the math I didn't want to have to do, but it was simple. What's the over under? Oh, I missed your message. Over under on Dijkstra. I don't know. Secretly hoping it's an LCM problem. Give me a sec. I'm messing with my keyboard here. Okay, so this is a new string. Well, new string. And I suppose we can just take new string and we can cons it onto search starting from I plus right dot length. Right? Yeah. This isn't ideal. This is not tail recursive. None of this is ideal, but like we're only going one layer deep, so I hope brute first works just fine. So we search starting from 1 or from 0. And now what do we call these new molecules? New molecules. And I'm just going to flat map this. And now that should give us a list of strings. So now we just take distinct.size val ans1 equals new molecules dot distinct dot size. Michael PC Gamer, hello. Wait, new molecules dot to list, I guess, dot distinct dot size. And Stack Overflow error. Okay, fine. Let's make it tail recursive. So search, we have an accumulator, list string. And then now our recursive search includes our new string. So new string onto ACK. Our string building is still not efficient in itself, but hey, that's tail recursive. And we need, oh wait, we need an end condition. That's why we didn't, that's why we had a Stack Overflow. Here, we don't need to make this tail recursive. We didn't have a termination condition. So we search from the new I. If this is -1, we shouldn't be doing anything. So if I is equal to -1, then we just return an empty list. Otherwise, we do this stuff. Okay, let's try that. Hofstadter, hello. Rodney, hey. Good to see you this year. Life has been all right. And Macaw, good morning. String has a patch method for replacing a slice. Oh, okay, great. Thank you. Are you a Scala developer or is that just from the JVM from Java? Uh, wait, what was the issue here? Okay, still Stack Overflow. I might want to make that tail recursive. We are almost out of time though. We might get to ends one. Let's make that tail recursive. But also having that patch method, whoops, might also make things efficient. Let me test it out. So we could have a string like X, a couple O's in the middle. So that patch from, okay, so you have your index. Ah, that's great. You do Scala. Excellent. Um, so we'll put that in, and let's just also make this tail recursive. So we're going to take medicine.patch from our index. The other string is right, and replaced is the number of things replaced. I might need to check the docs on that. Right dot length. Oh wait, no. Left dot length. Left dot length. Cool, that makes sense. Okay, a minute till my alarm goes off. Let's see if making this tail recursive makes it just work. So we have an accumulator, list of string. Okay, so new string goes onto that accumulator. And it's no longer out here. And we seed that with a nil. Brute force. And if this doesn't work, I gotta wrap it up and save that for afterwards. Okay, well, there's no Stack Overflow, so that's something. But it is about to time out. So we gotta make it more efficient. Alrighty. There are several things we could do. All right, there's our alarm. Good luck, everyone. I'm gonna get set up. Day 7, 2025. Let's save this. Oh, no, not that one. We want our day 7 worksheet. Save that as day 8. All right, thank you, Hofstadter. You too. 30 seconds to go. And Macaw, thank you for telling me about Patch. That's exactly what I was looking for. It had an unintuitive name. Oh man, I should have went to the bathroom before. Too late now. Here we go, day 8. Playground. We have a new understanding of teleporter maintenance. Elves are setting up a Christmas decoration project. There are electrical junction boxes. The plan is to connect the junction boxes with long strings of lights. Most of the junction boxes don't provide electricity. When two are connected by a string of lights, electricity can pass between those boxes. Okay. Most of them don't provide electricity. They're trying to figure out which boxes to connect so that electricity can reach every junction box. We even have a list of all the junction boxes' positions in 3D space. Cool. The list describes the positions of 20 junction boxes, one per line. Each position is given as x, y, z coordinates. To save on string lights, the elves would like to focus on connecting pairs of junction boxes that are as close together as possible according to straight line distance. Okay. Do I have a 3D point? I'm not sure if it's in my library. 3D, whoops. Whoops, what am I doing here? 3D. Um, there's a Z somewhere. No? All right, well, we're gonna have to make a 3D point. Hmm. Now, the two junction boxes which are close together but aren't already directly connected are those two. And then after connecting them, since that is already connected to another junction box, there is now a single circuit which contains 3 junction boxes. So wait, some of these are already connected? Okay, wait, we connect the closest 2. Okay, so we keep connecting the closest 2 that aren't already in the same graph. I see. So we have like a greedy connection strategy. Okay, since these two are already in the same circuit, nothing happens. This process continues for a while. The elves are concerned they don't have enough extension cables for all these wires. They would like to know how big the circuits will be. After making the 10 shortest connections, there are 11 circuits. One circuit which contains 5 boxes and one which contains 4. 2 circuits which contain 2 each and 7 which each contain a single junction box. Multiplying together the sizes of the 3 largest circuits produces 40. So we have many junction boxes connect together 1,000 pairs, which are closest together, but not already connected. Afterward, what do you get if you multiply the size of the 3 largest circuits? Okay, we can do that. So we need our own point case class point x int. You know, this is better input. Maybe some of these are huge. That's small enough. We can use int. So x int, y int, z int. And then we want dist to another point. Dist, def dist to other point. And that, I suppose, will be a double. Wait, what kind of distance are we talking about? Straight line distance. Okay. So this could be a double. Okay, so it's the square root of x squared plus y squared plus z squared. That's square root of x times x plus y times y plus z times z. Great. And it'd be nice if we could sort this in some way so that we are roughly, so we can like short circuit a search a bit. But for part 1, brute force probably works. So val boxes equals input dot collect. So this can be a list of point. Let's parse that. Oops. So we have an x y, and a z, all just comma separated. So point x dot to int, y dot to int, and z dot to int. And I suppose we repeatedly connect. We could put this all in one function. We need the closest two that aren't connected. So we need to keep track of the distance from each box to every other box. I don't want to recompute those over and over. Can we just n squared pre-compute all those? I think I'd like to. So val dist, this is going to be a map from pairs of points. um, I don't think the map's really necessary. We can just compute it on the fly. So we have a connect step, I guess. So Seafoams, hey, we are doing all right. Just getting started on day 8. So we have a bunch of boxes. We don't need to list the boxes. That's kind of global, but we have connections. Right. So connections is going to be, let's make that a set of tuples of point. And we'll have to normalize those by some ordering. We can just do by x, by y, by z. Okay, and then what else do we need to know about it? Yeah, we just need to know the set of connections. I suppose we want to know what we're connecting. No, we have to figure out what we're connecting because we're looking for the smallest distance that isn't already connected. Yeah, and we don't want to be searching for things that are already connected, right? We don't want to be searching for smaller distances. So this makes me think again that we should go back to pre-computing all the distances, sort them. Yeah, we sort those by distance. So dist, let's not even make a map. We're gonna make it a list of point to point, tuple of points, tupled with a double. Okay. Let's take our boxes. Let's normalize this a bit. We're gonna sort by um sort with less than no sort by, right. We just need to take our point and we can sort it by the tuple. So p dot x, p dot y, p dot z. That's a very natural way to sort it. Okay, so for um, for like a box A, so A from boxes and B from boxes. If A is not equal to B, we're going to yield A and B, and then the distance A dot dist to B. And then we're going to sort that by distance. So let's make a list there. So list dot from, and then dot sort by the ladder. And it's down here. Cool. I think that works. So we have pairs of boxes sorted by distance. And then we just build a graph of connections. Just compiling. Oh, hold on. It's possible that when I was running this day 19 worksheet, maybe I've killed stuff. No, this works just fine. Okay, so what's the issue here? File not found. It's not finding these files because of the class loader. Okay, I need to do a little bit of debugging real quick. It seems like the project's not compiling. It compiles just fine. So my class loader is not able to locate my files, my project files for some reason. I don't know. Okay, but the idea here is to just go down that list and keep connecting things. Right, and as we get connections, we spit those out. This is probably an unfold. Where the state that we're carrying over is the connections. Alrighty. So when we connect, we have a list of candidates. Candidates, which is going to be a list of point-to-point tuples with a distance. And I can feel my editor lagging out. Okay, my workspace is reindexing, so it might need to give me a minute. Let's kill this one. This is always fun when this happens. It's been happening to me a little bit this year, a little bit too often. Here, okay, we're evaluating now. We have a couple evaluations. I'm gonna cancel one of them. Oh, I guess that was the same evaluation. Well, that runs. Let's draft out what this looks like. So when we connect, we're gonna return, I suppose, a new list of candidates. The candidates we never considered. So in order to do that, we need to know which ones we can't consider, and that means we need the connections. So this is a set of point-to-point tuples, right? All right. And now I've just realized that here in our distance generator, we generate A to B, but we'll also end up generating B to A. So we need to dedupe that. And there's already a library method for this. So let's do boxes.combinations to map. So case, we have an A and a B. I think it's a list of A and B. In that case, we do the tuple A and B to A dot dist B. Okay, so that makes our quote shorter and also more correct. Is this sort by already turning a list? And it looks like my worksheet is still not back up. Okay, yep, we're back up and running. Sort by is now a member of iterator, right? Combinations is an iterator. We're gonna make that a list. Or we just move sort by out here. This thing already makes a list. Cool. Let that run. Looks like our worksheets are back up and running. This is not exhaustive. I'm just gonna make it collect so we don't get that error. Okay. So given connections and we have our candidates. Now we're going to return a new connection. So we're not going to type that. Let's type connection is just a tuple of points. In fact, we could just call them edges. Let's call it edge. That's shorter. Okay, so connections is a set of edge. And the candidates is a list of edges and that edge length. So what we're returning is a new edge and then a remaining list of candidates, which is going to be a list of edge. What am I doing? Edge and double tuples. All right. So we're going to take our candidates and we're going to filter. Let's do an iterator. We don't want to filter over everything. There's no need to filter over the entire list. We just want the first, right? So I suppose we can do a drop while. Candidates at drop while connected. So case edge distance connections that contains that edge. Great. And then the next one is just our edge, isn't it? Oh, no. We're not just looking at, no, we need the whole map. So we need disconnections to check that's connected to any connected component. So it's more complicated than that. And I'm at the point where I need to make a quick bathroom break, so I'll be right back. Hey, thank you. Thank you for letting me know. Yes, my mat was off. Um, yeah, so as I was saying, we left off, we realized connections isn't enough. We need to know if the two parts of this edge are in the same component or not. So I'm not sure if we'll still need this connection argument, but certainly we'll take components. And this can be a map from a point to, we could name each component based on the first element we put in it. So this could be a point to a point. Each component has just a, or this could be an int, it could be whatever. The point is that they're all named. Um, well, they merge. They merge itself. I suppose what we could keep doing is build like an adjacency graph. And we just update that. So this, in this case, could be a map from a point to a list of points, maybe a set of points. And still, like at some point, those merge, but we still get, it's still nice to have it based on this. Well, we have to follow the adjacency graph. We basically end up doing like a depth first search in that graph until we maybe don't find the other point. Maybe we should just have a set of what it's connected to. So what it's connected to could be a map from a point to a set of point. I think it's reasonable to build and maintain that, right? So this is actually just the first part of connect because I want to keep these functions smaller so that we can test them. This would just be called like next edge, next edge. Hmm. Okay, and then we drop as long as they are in the same um, component. All right. So let's do A, B. Drop while connections of A. A is basically connected to B. And then that means our new edge can come from this and remaining. So we can just destructure that list, new edge and remaining, and that's what we return. All right, new edge onto, oh, let me, okay, I'm happy with that. That should work for us. And then we need to figure out how to make a connection. We should look at what our broader, how we're planning to use this whole thing. So we repeatedly make connections, right? And then at some point, we still have to like, we have to dedupe as we're making these connections. So def connect, um, and we'll just call them A and B. So points A and B. A is a point, actually. Point, B, point. No. And we have a connection map. So point to set point. And then we have this returns us a new connection map. Map point to set a point. So we take our connections, and I suppose what we could do. I was thinking about like removed A and then update B to include A. I think we kind of need this. This isn't just the components, right? We need to be able to connect every, like, given an arbitrary A, we need to know it's connected to. We're just gonna write that out so it's more obvious. So I guess we just update both sides parallel. There's some place at which we're gonna have to dedupe these. I don't want to have 1,000 different um, sets that are identical. Um, I'm not sure I like what I wrote myself into. Well, I mean, there's an obvious implementation. We could just do conda updated. Um, so A gets con A plus B, right? And then we do the same update symmetrically for B. Yeah. Okay, well, we're just gonna have a lot of tiny sets floating around, I suppose. Maybe if there's some way we could normalize A and B, like we know which one to look for. Like it should always be in one direction. Right, now we already have our boxes sort of already in an order. Right, like all of our edges go from one to the other, from an A to a B. Yeah, since they are already ordered, we have some sort of normalization. We can assume that A is the one that should keep its list of connections. I mean, B then shows up, B then has like another list of connections. So that gives us a partial ordering. It makes it a directed graph. I don't know that that's helpful for us. Because we have to have the other direction to see if in fact things are connected. I just don't want to do so many searches. I want to have stuff cached, and I also don't want to have I want to have everything cached. I don't want to flood my memory. Uh, we're gonna go with flooding my memory for now. So we still have to figure out the deduping problem at the end. Um, so I suppose we're gonna make repeated connections. Everything starts with an empty map. We can just iterate or dot iterate here. So our initial state, well, no, we have more state in our search, right? We have our list of candidates that we're going down in order. So let's make this an unfold. So our initial state is dist, which is a list of candidates. And we also have a map.empty. So this is the point to set of point. This is our connections. Okay, and we don't really have a termination condition, I suppose. I suppose it'd be like when everything is connected. Broad and white, thank you for the follow. Okay, so we have our state, which is our connections, or I don't know, this is like a connected graph. Connected, and we have our, well, we have our candidates. So our candidates are first. Okay, and I suppose at this point, the candidates don't need the dist. So they're just sorted by the distance. Why can't you use your ponats? You mean your points? Um, because I'm not an affiliate. So I don't have channel points. Basically, I just don't want ads on my channel. So to have channel points, you have to sign an affiliate contract and let them put ads in your channel. And I don't like that. I don't like ads. Okay, where was I? Oh yeah, thank you. I appreciate it. Um, where were we? We keep connecting a next edge. Oh yeah, we were talking about how we don't actually need the distance here in our list of candidates. So our list of candidates is just a list of edges. That's all we need. So we'll need to structure this. We don't need dist. We were never using that. As long as candidates are already sorted by dist, we are good. Um, call this edges. So we're renaming this to edges. And we're basically taking boxes, combinations of size 2, dot collect. We don't need this collect. So we make that to list dot sort by. Oh no, we are going to do a map on this because we want tuples. So case list A and B. We're going to make that a tuple A to B. Make that a list and sort by. Given A and B, we want A dot distance B. So we can just write that as underscore dot distance underscore. You want to make games when you grow up? Game dev is a lot of people's motivation for becoming programmers. I'd be lying if I say that wasn't an influence on me. Okay, what's going on here? Oh, our types are not aligned anymore. We don't need that extra double. And returning edge and a list of edge. Okay. Yeah, basically we just drop all those connections. What am I making? So we are solving advent of code. Solving this problem. This is a calendar of puzzles, programming puzzles. Every day at midnight, a 2-part puzzle drops, and tons of people get together and try to solve them. So if you look around on Twitch, there are several other streamers doing the same thing. Okay. I'm happy with this. That's a spurious error. Okay, so we have our candidates, we have our connected graph. We are going to find the next edge to connect. Next edge. No, we have an edge. We have remaining candidates, and that's just from the result from calling next edge given connected candidates. Um, Unfold's always going to work. I'm going to assume it always works as long as we want anyway. So this whole thing gets wrapped in a sum, and we have some sort of output. Our output can be the states of the connection graph. And then we have to carry along our state, which is the remaining candidates, as well as connect. We need to make our new graph. So we connect A and B. I just want to pass up the edge along. So we're going to connect the edge in the graph connected. Okay, so this is going to be an edge about A, B edge. No, I'm not making any games. For now, I'm just focused on this puzzle. But I'm a software developer for my day job. Um, Great, so these are all of our states. Val states. End state would be states.drop 1000. Yeah, drop the first 1000. Okay, so that runs just fine. Now we just need to dedupe. So basically for each end state is an iterator. Why is it an iterator? States is an iterator. Oh, dot next. Okay, so end state is this map. What we could do to dedupe, no such element exception. There's a key that's not found. Oh, right. Our map needed to have a default value. Out with a default value of an empty set. I do. I've written Scala in production for about a decade now. Which is a long time in Scala years. I've seen communities rise and fall. The Scala community had a lot of drama. Okay, so now we dedupe this. What I can do is just take any point and all the points that's connected to, I'll just remove from the map, and then we continue. So I suppose we could take boxes dot fold left, and we start with that end state. Okay, so we have our accumulator, and then we have some point A. Yeah, if anyone wants to get a job in Scala, talk to me sometime. Or if you want to learn, happy to help. So, do we do this? We're gonna take act, look at A. So these are all the connections. Val, um, everything that's connected to A. And we can take that and use it to modify ACK. So connected to list fold left, start with ACK. Okay, so we're gonna shadow our previous ACK. And I assume a point doesn't show up as connected to itself, right? We could make an assertion there, just that the bug shows up. Assert that B is not equal to A. Right. But what we're really doing is act dot removed B. Remove that key. Okay, and we're only doing this if A is even in ACK. So if A dot contains ACK, or the ACK contains A, then we do all this. That was wise. Just return ACK, else ACK. Okay, that should dedupe things, right? So these are our components. Val components. What is this map? This is isomorphic to any kind of different component graph you might get. It seems like we have a problem here. Oh, no, that's not a real problem. So now our answer, three largest components. So components dot values dot map. So each of those we want the size plus one because the key is not in there. Dot take three. Wait, we need to sort it. Dot sorted. Dot. No, we need to sort by size. No, we just take the sizes. We take the three largest sizes. Great. We take the three largest sizes. So I'm going to take right 3 and then product. Val ans 2 equals that. I think we've got an answer. Sorted is not a member of iterable. Okay, so values to list then. Or you know what? We could have done the to list after making it int. Either way, we have an answer. 166,420. Okay, not quite right. 166,420. Let's test it on the. Let's test it on the example. And in the example, it's only after how many connections? The 10 shortest connections. Okay. So in the example, we'll only do 10. I'm going to forget to change that. I'm calling it out right now. So if I have bugs, please remind me. Uh, all right. Let's run with the example. Ands 2, this is ands 1. We're not done yet. Okay, we got the answer 11. That's not quite right. So let's take a look at the components. That's not pretty. That seems to be implying there's only two components. Or there's only one? Yeah, there's only one component. Well, let's take a look at the end state. So we made 10 connections, right? I just wish our points were numbered so we didn't have to look at the whole thing. Interestingly, oh, I see what's happened here. When we build up the sets, we don't do it fully symmetrically. Okay, so when we make the connection, um, yeah, when we update the connections of A, we can't just add B. We have to add everything that B is connected to. Um, they both essentially become A union B. So con A dot union con B, then plus B in that case, con B dot union con A, and then plus A. I don't love it. There's so much redundancy in the data we're storing. But as long as we have enough memory, I guess we're fine. Okay, now let's take a look at what this looks like. Maybe now we'll find like a logical error. Um, we're gonna have to tear that down a little bit to examine what's going on. But let's also just take the three largest. So let's see what components looks like. It's still just one component. They're all basically connected to the same thing. Okay, why don't we list each connection we're making as we're making that connection? Um, connecting edge. Yeah, and then we'll copy that worksheet output and do some investigation. Now where's the part where we printed out the edges we're connecting? Here's the end states. Um, did we ever get this? You'd think when we drop 10, those would show up, those print line statements. An alternative, we could just return the edge that we connected. We could return the full list of edges we connected and then do something with that. But also for the purpose of debugging, we, we'd like to do that. So connections. And then we'll just print those in order. Connections.take 10 for each print line. All right. Okay, so these are the connections we are connecting in order, and we are repeatedly connecting the same point to many other points. So maybe there's something wrong with the distance function. Alrighty. In this example, the two junction boxes which are closest together are 162817 are these two. So those aren't even the closest together. Okay, well, let's look at what we've sorted then. So we have these edges. We take combinations of two and we sort them by distance. Why don't we print all of those edges along with their distance? Uh, edges dot for each print line. So we'll just load the edge and then let's call this case edge at AB and unmatch that as well. Now we can put a dot this B in here. That's not a member of what's going on. Oh, go. Okay, let's look at that output. Okay, these are the smallest distances. 117. There's something wrong with our distance function. Why are these the same? Okay. Let's have a look. Um, Wait a second. I just okay, for a diagonal, it's square root of a squared plus b squared, right? Pythagorean. But for a diagonal of a cube, let me think about this. So there are we want the diagonal of the plane that sits diagonal inside the box, right? So one side of that is going to be that, and the other side of that, so that's one side length. The other side length is going to be z. And to get the diagonal of that, we square this, and we square this, and we get the square root of that. Okay, yeah, that's right. That's square root of that. That is the distance between 2 points. Oh, hold on. It's not x times x. It's x times the other x. And then other dot y. And then other dot z. There we go. Fixed that. Okay, now let's look at the worksheet output. In fact, you know what? The answer's probably just right. Let's look at it. Okay, the answer's still wrong. Right, it should be 40. But things probably look a little bit better. Thank you. But you know, part of the reason I've coded in public is I want other people to catch that for me. uh, okay, so our connections in order. The closest two are, we're not getting the same answer. 5, 4, 2, 2, 9. Yeah, the two junction boxes are closest. And we are using the example, right? Yeah, we are using the example. And the farthest away is these two. Oh, fuck. My distance is still wrong. We need the delta for each of those. Okay. All right. Dist. Man, I cannot math. So val dx equals x minus other dot x. And then val dy. I'm renaming other. It's just gonna be another point p. Y minus p dot y. Val dz equals z minus p dot z. And then it's each of those squared. Dx times dx. Good catch too. Yes. Dy dz times dz. Okay. Now I believe that's fixed. I'm glad we're debugging this though, not performance. This is so much nicer than debugging performance. Oh wait, we add those. Man, that kind of hurts my eyes. Cool. Now we have a different answer, but we have components. So let's look at the output, see what connections are being made. Okay, so here are the edges in order. 162, 817, 812. That's this one. We are now connecting them in order. Cool. Great. Now I just want to know the edges that are being connected. So here are the connections. First, we connect those two. Great. Now the two junction boxes, which are close together but aren't already directly connected, are 162 and 431. This one. Great. Next two junction boxes to connect are 906 and 805. Great. The next two junction boxes are 431, 425. Cool. So we're still connecting them correctly in the right order. So I'll believe that's working. But after making the 10 shortest connections, there are 11 circuits. One circuit contains 5 junction boxes. So here's our end state. This is, oh, and we have here's the list of connections earlier from our print line that we were expecting. End state, we should group those by size, but there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Well, hold on. That's not going to tell us anything. We want to know how many circuits there are, so we reduce the components. There are 5 circuits. No, there are 11 circuits. So we have lost some circuits along the way. Um, but let's count this. So this, which is connected to these other two, there will have been two connections here, right? So 1, 2, 3, 4, 5, 6, 7, 8. We're only seeing 8 of the connections there. So something's gone wrong before this point, because we would see more points in these sets. Um, let's go back to the drawing board over here. So we don't need to print this anymore. We have our end state. If we made 10 connections, there should be well, there could be any number of points affected, which could mean any number of, I don't know, elements in this map. But when you make the components, are we doing that correctly? So, we have a point A. If A is still in there, then we can remove its connections. So we have all of its connections here. And for each of those, we don't need this assert anymore. That's not failing. For each of those, we remove it. Great. And otherwise, return that. This, we could test that. I feel like that's probably not where our bug is. So let's look at what each point is connected to. Now, we didn't get all, it didn't tell us all of the connections, but we know some of them. So for example, okay, there's a group of 3 somewhere here. So 162, 431. Okay, looking at our end state, let's look at 162. What's it connected to? 162 is connected to the 425 and 431. Right, 162 is connected to 435 earlier. Okay, and this 431 is connected to 425 and 162. So that component looks correct. Now the 425 should also have that mirrored, that same information mirrored. 425 is connected to more points. 162, 425, 431. Ah, I know what's wrong. When we make this connection, it's like fully recursive. Okay. We need to do that for every connection in those. I don't like that. So we need something that's more compact. I guess we could just leave it at an adjacency graph and do a depth first search in there. Or, just a full search for another point. Um, Yeah, let's just track direct connections. We'll just have like a proper adjacency graph. And this is not the whole set of components. That I think is more sane. That's probably what most people are doing, honestly. Um, so con A, not gonna union con B. We're just gonna add B in there. And similarly here, we're just gonna add A in there. Oh, okay. So we have a way to connect. Um, now when we determine next edge, we need a better way of determining that two are connected. So con A that contains B is not enough. So if con A has everything A is connected to, we can just search recursively there. We'll put the search algorithm in here. I'm fine with that. Well, actually, we might need to make it a function because it might need to be recursive. Def connected. So is A connected to some B? A point, B point. And then we have an adjacency graph. So edge. I have a few different names for the same concept here. So I apologize if that's a little bit confusing, but basically they are all adjacency graphs. This is a map from point to set of point. And this is going to be a Boolean. So check things that are adjacent to A and see if there exists among them an AA such that A is equal to B. Yeah, the points have to be unique. Or AA is connected to B via the same adjacency graph. Yeah, we can write this in a different way. I think I'd rather check first if adj contains B. So adj contains B, or adj A that exists in AA. Then we don't need to have this connection here. I'm just going to put that in line and make a recursive call to connected. Okay. In the same adjacency graph. And I hope when our graph gets big, how large, how many, I'm hoping we don't hit a Stack Overflow. I don't think we will. Because that would be a depth first search. And there are other nicer ways to write that if that is the case. We can make it some sort of flood fill and keep looking for B in a set or something like that. And it can be tail recursive. So plenty of ways to optimize this if we need to. Okay, now we need to use this connected. So basically we do this if connected, A and B. A and B are connected in the connections. Okay, I'm going to rename this to edge. Rename symbol adjacency graph. Alrighty. And this is also edge. Stack Overflow error. Okay, well, I already know where that's coming from. That's coming from this connected search. So we have a B that we're searching for. Let's make a tail recursive search function here. So def search. Let's have a visited set of points, current set of points, and it's going to turn a Boolean. Okay, so we're going to take current flat map by the adjacency graph to get another set of points. We're going to diff out points we've already visited. And this is our next set of points, so val next. And then we're going to recurse with search next. So next becomes the visited. Well, we know current becomes the visited. And then next becomes the new current. Great. Now that's going to be an infinite search. We need to actually look for B. So current dot contains B, or we recurse. And if current ends up empty, then it has to fail, right? So let's say current dot non-empty and current dot contains B. So once current's empty, then that just has to fail. And let's see here. And that should do it. That is tail recursive. So we can search. Visit starts off empty. And current starts with point A. Doesn't like that in the middle of a phrase. So we'll do this little trick. Current should be a set of point. There we go. Okay, that's just a flood flow. There are other ways to write it, but I went with that. Okay, we're back to having it run. Now let's look at our end state and see what is connected to what. So in particular, we're interested in our 3. So 4, 3, 1. Oh yeah, this is just an adjacency graph now. And then now we have to search for the largest components. So now in our components, we're building components. So end state is our adjacency graph. And can we basically turn that into No, we need to make it a new adjacency graph. Blesploit. Blesploit? Thank you for the follow. And welcome to the stream. Okay, so we're going to take our boxes and we're going to make a new map of components. Um, I guess this could just be a list of sets. Yeah, it's a list of sets. So list.empty of sets of points. Okay, so we're given some A. I'm going to rename this to an adjacency, whatever. We know it's an adjacency graph. So we look at what's connected to A in end state, and we search out a component. Let me just comment this stuff out so it doesn't get in our way. So to get a component, def component, starting from a point, and we give an adjacency graph, which is a map point to set a point. We're going to return just a set point. And basically, we just flood fill until we can no longer flood fill. So I'm just going to copy our earlier flood fill code, our search, and modify that slightly. Okay, so the search is going to be, let's rename it to flood fill. Flood, it's going to return a setup point. And it's going to be a continually growing set. It could be a union of pieces of a set. No, visited will keep growing. Once current is empty, then we return visited. Yeah, I like that. So if current that is empty, then visited. Else, next is that, and we search. So visited is a growing union. Visited dot union with current, and then we are continuing to search from next. And that there works. Now, while I was doing that, I was wondering if I should be unioning visited with the previous visited.union. Right. Maybe we get away with it. Like sometimes you do, if it's a grid, for example, you don't have to union it with the current. But in this case, we don't know what could be connected to what. So we'll leave that. Okay. So to get the full list of components, we get the components of A, and then for everything that is connected, we remove that from our list of things we're planning to connect. Right. So we have a bunch of remaining points. This doesn't really work with the fold left. I guess it can. This can work with the fold left. So we ignore it if this accumulator already has a component that contains it. So if ACK that exists, component C such that C dot contains A, then we just continue with that accumulator. Otherwise, we add a new component. So components, component of A in our adjacency graph, which in this case is end state. And let's see. Oh, that's all our parameters. And then we const that onto our accumulator. Okay, that works. Search. This is actually now flood. All right. Now, how many components do we have? We should have 11. We have 10. That's close. Let's see what answer we get. Components dot map size. No. We make that a list first. To list map size. Take the right 3. Okay, now it's still a problem that there are 10 components. So let's take a look at these components we printed. Let's print the sizes of each component. So components.map.size for each print line. Okay, 1, 2. So most of them are 1, and then we have 2, 5. There are 11 circuits, 1 which contains 5, 1 which contains 4, 2 which contain 2, and 7 which each contain a single junction box. Yeah. 5, 4, 2 should make 40. And instead, what we're getting is 5, 5. So one of those is too large. Okay, let's take a closer look at this output. So we know some of our special ones. So this 431. Let's find 431. 431 should be connected to 425. And what was the other one it's connected to? And 162. So it is connected to those, but it's connected to a few extra here. Maybe that's fair. Maybe it's supposed to end up connecting to 2 extra. It doesn't tell us that there's a circuit with just 3 junction boxes at the end. Let's look at the sizes of each component and sum them up, because we should get the same number of boxes we started with, right? So that's an easy test. So map size, whoops. dot sum. And then we had boxes dot sum. Oh, maybe we're just like one connection short, like an off by one, some boxes dot size. Yeah, maybe we had one too many connections. Uh, yeah. Right, like how many edges did we connect? Let's look at this. We'll copy worksheet output and look at how many connection messages we got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's it. We just connected too many. So it's drop 9, not next. Okay, and that gives us 40. Great. Well, now let's do 999 along with the normal problem. I think we've got it. As long as it's performant enough. There's a lot of traversing through graphs in here. And there's a lot of redundancy. Well, I mean, we have an adjacency graph and we track both directions. Timeout reached. Okay, timeout reached, but also I kind of have enough faith in this one that maybe we can just YOLO it and let it run in the background in a different process. So package 2025 main def day 8 turns a unit. Print line ends 1, and let's take out all this unnecessary code. That is a lot of unnecessary code. Like we're pretty verbose, aren't we? Um. Okay, that should do us. It's not liking something here. Illegal start of top level definition. Oh, we need a colon here. There we go. Wait a second. Sorry, we need an equal there. All right. Let's give that a run. Yeah, that's fine. So it's gonna be run main 2025 dot day 8. Wow, it's already 1:30. This is taking longer than I felt like it did. Oh, I was such a roll during my warm up. I didn't expect to take this long. Uh, But we've been smooth enough, I suppose. We haven't really choked on anything. SB could not. There's another instance of SBT running on this build. Oh, wait, what? I assume we're just using the same instance then. It's just always gonna have a single daemon then. Um, and while that's happening, we can look at how to make this faster or more efficient. So what's our performance um, bottlenecks here? So when we're looking for a next edge, we're checking if, oh wait, the print lining is not a great thing. Let's stop that. Print line really slows things down. Are there other print lines? Okay, we just want that one. Okay. Back here. So when we're looking for the next edge, we are checking if edges are connected. And we do that by like flood filling through the adjacency graph. If graphs get huge, then that gets slow. Well, it's not going to recurse too many times if this is pretty wide, I suppose. I suppose on each iteration you might only be connecting to one other. I suppose I could throw in random spurious connections. There's no rule against making more connections than necessary, as long as they have the same components. We're still compiling and compilation is slow for some reason. Uh, there's that. There's also when we are finding the components at the edge, we do like a flood fill recursively on each of those. But we're not doing that for everything, right? Specifically, everything that we find ends up getting removed from the list of candidates, right? It gets filtered out. This is going to be slow if we have lots of individual components. So we could instead build a list of things that are already, a set of things that are already part of a component. Yeah, I think this can be a lot faster if we don't use a list. That's an easy win. Okay, let's try something like that. Um, and in that case, it's not really going to be a fold left. I mean, I guess we could still be a fold left with like a scene set. But I think this is more of an unfold. We have a state, which is our set of unvisited points. So let's do iterator.unfold. Well, what would unfold return? It would return like a series of sets every time we make a set. Yeah, sure. So our initial state then is all the boxes.toSet. Um, and that will be our unsorted. So keep going as long as unsorted is not empty. So option dot unless unsorted dot is empty, then we find new things to return. Then we get a component, val c equals component. I guess we take an element, so val a equals unsorted dot head. What's wrong here? So component from A, and we're using end state as our adjacency graph. Yeah. And we return that C, and our state becomes unsorted dot diff C out of it. Okay, great. And then we turn that whole thing into a list, and we're golden. Oh, our YOLO is still running on the right, but let's try this. In the worksheet, let's let that time out. And then after that, we could try it on the example, make sure it's at least correct. But I think this is still correct, and it's a strict improvement over what we had before, right? And these states, we are creating a lot of maps. We should maybe just do this in a mutable way, keep updating a map. What we're doing is repeatedly getting the next edge and then connecting that edge. Connecting that edge is pretty fast. We just add points symmetrically in the adjacency graphs. Maybe the fact that we're using so many hash sets is expensive and we should just use an array. If these sets aren't getting very big, yeah, I think we're at least conceptually correct, and we just need to performance optimize. Okay, yeah, that is getting the correct answer there. I'm going to copy this over to the YOLO, and I'm going to restart the YOLO. Oh, what happened? List, wait, match error? Match error where? Huh, that's interesting. It actually failed. Okay, let's take a look at that. That is a potential bug. So at next edge 35, oh, this thing. Um, wait, how can this? Right. we might return an empty list. If candidates is empty, okay. So if candidates is empty, then there is no next edge. So wait a second. How do we get to the whole list of everything? I mean, let's go back to this worksheet here. Let's prevent this from running. I just want to know the size of our input. So val components, all of this stuff, we're gonna comment that out. Our calculation of end state, we're gonna comment that out. How's admin code going? I think it's going all right. Something that works. We just have to optimize it. We have a kind of very heavyweight program here. Or I'm pretty sure it works. I found just one edge case bug here. We'll handle that in just a second. Okay, so our worksheet is live again. I want to know how many boxes we have, how many edges there are. We don't need to print this anymore. Edges.size, box.size. And this should be well over 1,000. I mean, if it's even over 2,000, then we should not hit the end of our list of candidates. So that bug we saw here, this should not happen when that's empty. Right, this fails when there is no next edge. But we shouldn't be calling for a next edge, like, right, now the only way a call for a next edge can fail is if we're trying to build more edges than are possible, right? There are 500,000 edges possible. We're only making 1,000 connections. Okay. I do kind of like this printing. I want to keep track of the number of edges so that we can see our progress. So far, n equals 0. N plus equals 1. And then we print that here. And connecting edge. And then this components definition, we want to take the more efficient version from the worksheet. So go to worksheet, get components. At the end, it's commented out. Okay. Let's give that a shot. Now we have some printing. So we can see this as it's connecting edges one at a time. And it's numbered. So if we're connecting more than 1,000 edges, we should we should know it. Okay, it connects 1,000 edges. And then at this point, it is stalling. That is interesting. So I think we're able to get the end state then. Um, right? That only prints once you get all through those 999. So then the slow bit is still this creation of all the components. Okay. So let's print line there. Found component. Found component C. Okay, we make 1,000 connections. And for some reason, this is slow. It's not slow, it's infinite. We're not even printing a first component. So our component function here must be recursing infinitely. Um, this is tailrec, right? Annotation dot tailrec. Just throw that in. That doesn't make it tailrec, it just verifies that it is tailrec. It fails to compile if it isn't. Okay. If current is empty, then we return visited, right? Otherwise, current flat map adjacent diff visited. And then we union visited with current. And that can get pretty big if you have a component that is 500. You could end up with 500 calls to, I mean, 500 is a lot. The biggest component here, let's say there's like 100 in there somewhere. 100 recursions on this, unions of two sets. In the worst case, it's like a tiny set of one element. I don't think that should be bad. So we're taking current, we're flat mapping to things that are adjacent to it, but we're diffing out the things that are already visited. So we're not going to go in a loop. And that worked fine earlier. I mean, that worked fine with the example. So I don't think we're in an infinite loop. I think we're just in something that's really slow. Okay, let's see how fast it's happening. So let's do a print of blood and then visited. Well, let's look at visited.size. And then after that, we'll say like found component. So we can watch the flood size grow, and that'll give us an idea of the shape of the graph. I'll make this bigger on the right so we watch it together. Okay, there we go, 1,000 connections. Now we should be flooding for the first component. Um, Wait, shouldn't there be a 1000th connection? Because 1 numbers the first edge, right? So we should be connecting 1000 edges, and this starts at 1. And it's worrying to me that we're not seeing this flood. So after this point, okay, am I somehow running this iterator longer than I need to? I mean, it's not printing that. Let me at least get a print line here. Just want to make sure that this actually is ended. Searching components. Okay, I'm gonna run that again, and I need to go use the restroom, so I'll be right back. Yep, and we're not getting to this statement here, so that worries me. Okay. Okay. So this is still running something. I don't know what code it's running. Because as far as I know, it prints these 999. It should be getting to this line next. Unless somehow on 1000, maybe this should be 1000. Unless somehow on 1000, then it's choosing to infinite loop when we try to connect. I don't see how that's a thing. I want to see what this output looks like for the example. So let's try the example. We know if that runs long enough, eventually it'll run out of candidates. That's the behavior we saw. So it was going through a list of candidate edges and continuing to try and connect those. In which case I don't understand why it ends just fine on the example. Okay, so this is what a run should look like. All right, 1 through 10. So we should see 1 through 1000. And then a few floods. 5, 4, 2, 2. Okay. Um, hmm, that's totally fine. All right. So why does that continue on that edge in particular. What's special about that edge? Um, we don't even get to this line. So when it's 999, I want to know maybe everything's already connected. So after we made 999 edges, are we then abandoning candidates? So next edge is failing, and next edge would fail if it turns out that our A is already connected to all the B's for every AB. Okay, so let's just put a special case here. We don't use breakpoints and debuggers here. We just use print lines. And once we get to 999, let's print our current state. Okay, so what kind of things do we want to know about at this point? Adjacency graph. I guess we could print everything in the adjacency graph. How many things every edge is connected to? We could look at the size of the candidates. So we're going to do all of this only if n is equal to 1000, that final bit. Okay, so I'm going to print candidates remaining. And it's that size. And connected here is our adjacency graph. We could rename this connected. It's just an adjacency graph. Okay, and then edge dot to list dot sort by the number of points it's connected to. 2 dot size, and then dot for each. We're gonna print. So case point, and then various other points. We're gonna do print line. Whoops. Print line of P connected to P's dot size. Okay. That could be some helpful-ish information. And then we'll turn debug on. So we could have two versions of this. And the else case runs it without debug. Yeah, there's definitely a nicer way to write that. debug equals true. Let's go to our next edge definition and let's add a debug. Debug Boolean defaults to false. And now for debugging. Then for each of these, we're going to talk about the edge that we're checking. Print line, well, if debug, then let me print line checking A to B. Yeah, that's fine for now. All right. We're back to 999. Let's give that a shot. Okay, so we're checking many different points. Crap, that was too much printing. We can't. All right, let's cancel that execution. I need to see. It's still growing. We're not going to be able to scroll back to the other debug stuff. All right, this was too much printing to do. We're just going to ignore that. You want to see this stuff first for sure. Alrighty. So we make all our point connections. All right. And then we get to candidate 1000. Okay, now we're making the 1000th connection. And at this point, we have at least 999 connections. Most of these earlier ones are only connected to one other. Okay. And if you connect it to 2, 3, and then the largest ones are connected to 7. And I imagine the sum of all those numbers we're seeing on the right is 999. And why is it so hard to add the 1000th point? I don't think there's a broad performance issue. There's like a degenerate case in here somewhere. I don't know. If anyone has a thought, I'd like to know. Because this is a little weird. I guess each of the edges. Whoops. Okay, what we could do is look, are there any that are not connected to anything? When we get the next edge, we check um, if A is connected to. Oh, temporalis. Welcome, welcome. How was your night? Um, I'm still in part one. Hey, so I'm still in part one here. I've gotten it working, so it works for example case. It appears to work for um the problem case until we're drawing the 1000th edge. So really weird. We can make 999 edges. And once we get to the 1000th edge, it decides that all of these are bad candidates. So we get here, there are 500,000 candidates remaining, and it doesn't like any of the following candidates. So it searches through the entire candidate list to the end and crashes at the end of that. You've forgotten everything you knew from college about graphs and stuff. Um, well, I wrote up this piece of not working code pretty confidently. I don't feel too stumped by this problem. I feel stumped by this bug. We can make 999 connections. When we try to make the 1000th connection, it decides none of the edge candidates are good. You know, we could. I just want to see if my code at least will work if we only take 900, you know, if we take one edge less, right? Let's drop that down to 998. See if we can get an answer for that. Okay. To find where the logic broke. Yeah, I'm gonna have to do that. Except I don't think I'm gonna find that logic breaking in my example. I'm gonna have to look in here. So I'm gonna have to stop the state at 999 and then do some like worksheet assisted exploration of the graph state at that point. Um, and also, does this? Okay, this gives me an answer if I take one less. So my components, what do my components look like? We have two components. Everything's connected. We have one component of size. Huh, interesting. Okay, that looks like a, that could lead us to a bug. Two components, one is size 999 and the other is size 1. Everything's connected after 1000. Well, how many boxes are there? There are only 1000 boxes. Oh, so okay, well, now we know where our program is crashing because once we get to this point where we've made 999 connections, we've connected the entire graph. So for that final connection, it literally can't find any, everything's already connected at that point. Um, but I mean, of course, if you do 1,000 connections, right? Okay, let me just pull up. This tells me maybe I'm misunderstanding part of the question, right? Let me, I need someone to double check my logic here. So let's say, um, oh, okay, let's say you only have 5 things. 1, 2, 3, 4, 5, and you're going to make 5 connections. Then make 1 connection between 2 things that are not already connected. Make another connection. 2, 3, 4. You can't make 5 connections. So if your input only has 1,000 and you're asked to make 1,000 connections, that's impossible. Right? That's what I'm running into right now, which tells me I'm just misunderstanding the problem. So someone correct my understanding of the problem. Connect together 1,000 pairs of junction boxes, which are